Let's talk a little bit about metallic solids. And here is an example of what a metallic solid might look like. They tend to be shiny like this. Some would say lustrous. Some of you might be guessing maybe this is some type of aluminum or silver. It actually turns out that this is sodium. Our same friend sodium that we saw bonding with chlorine to form sodium chloride and form ionic solids, it can actually bond with itself with metallic bonds. This right over here, you might guess is silver or something. It actually turns out this is calcium. And I know what you're thinking, isn't calcium kind of this chalky white powder? Well, no, those are compounds formed with calcium, things like calcium oxide. But this right over here is pure calcium. And the reason why it has to be in this container, it is highly reactive with oxygen. So that's not oxygen that is in this container. It's some form of inert gas. But calcium, when it just bonds to itself with metallic bonds, which we'll talk about in a little bit, it also looks kind of similar. It's this shiny, metallic, or lustrous look to it. And what do you think this is? Well, this is something we're used to associating with metals. This is gold. But once again, you can see it has this lustrous property. So what is it about metals or metallic solids that allow them to be lustrous in this way and have other properties that we're about to see? And to understand that, we just have to look at the periodic table of elements. And most of the periodic table of elements is actually some form of metal. You have in red right over here, the group 1 elements, not including hydrogen. Those are your alkali metals. Then you have your alkaline earth metals, your transition metals, your post-transition metals, your metalloids. And it's really only what you see in yellow and blue here that are not your metals. So how do metals form solids when you just have a pure sample of them? Well, the general idea, you can look at your alkali metals. They all have that one valence electron. And to get to that stable outer shell, it's much easier for them to give away a valence electron. And that's why we often see these folks participating in ionic bonds. They can be ionized quite easily. But if you have a pure sample of them, they can contribute electrons to a sea of electron, one each. These alkaline earth metals, they have 2 valence electrons. They too can be ionized, or if you have a pure sample, like in a calcium, they can contribute 2 valence electrons to a sea of electrons. And the transition metals here have a similar ability to contribute valence electrons. And so, in general, we can view metallic solids as having cations, these positively charged cations, in a sea of electrons. So you have all these electrons here. I'll just try all these minus charges that they're in. Where does those electrons come from? Well, if you're looking at the alkali metals, each of those atoms could give 1 electron to that sea because it doesn't really want that valence electron. If you're talking about alkaline earth metals, they can each donate 2 electrons to that sea. Now, given that you have this positive charge in this sea of electrons, what do you think are the properties? How good do you think this will be at conducting electricity or heat? And many of you might guess, if you looked at a wire, wires are made out of metals because they are excellent at conducting electricity, or they tend to be excellent at conducting electricity because you have all of these electrons that can move around. And so if you apply a voltage, they will start moving and conduct electricity. And those electrons can also be good at conducting thermal energy or heat. Now, we already talked about them having this shiny, lustrous property, but how easy would it be to bend them? With ionic solids, we talked about they can be strong but brittle. As soon as you try to shift them around a little bit, they can break. But what do you think is going to happen here? If, let's say, right over here, I were to push really hard, and on the top, I were to push really hard to the left. Do you think this will be brittle, or do you think it will be malleable? It's easy to bend. Well, if you have a pure metallic solid, it's actually quite malleable. If you just took this top part and pushed it to the left, like this, no big deal. You have those cations that are still in that sea of electrons. And that's generally true of metallic solids. They are very malleable. They are not brittle. In fact, so much so that oftentimes we want them to be a little bit more rigid. We want them to be a little bit harder. And that's why we might do things like add other elements into the metallic solid. For example, pure iron is reasonably malleable, but if you want to make it stronger, you could stick carbon atoms in between. For example, you could put a carbon atom there or a carbon atom over there. And that way, it kind of disrupts this electron sea a little bit, so it's not quite as malleable, and it'll be stronger and more rigid. So I'll leave you here. This is just an extension of what we've already learned about metals and metallic bonds to just realize why most of the periodic table of elements that we're familiar with has some of these properties when you have pure solids of them.